So hey everyone, today is the 15th of June 2013, and today I'd like to share with you a video that I found to be quite amazing. So let's get started. So suppose I have a circuit which is the following. So I have two resistors and I connect them to a 1 volt EMF battery. So the positive terminal would be here, and I connect them together. Let's say this is R1 and this is R2, right? R2, let's say that is 900 ohms, and R1, let's say that's 100 ohms, right? So this is a 1 volt EMF battery. So I connect the following arrangement. I label these points D and A. There's no particular reason I chose these values, 100, 900, or 1 volt. You could choose either um, any value, and the result would come the same. All right. So we all know Ohm's law, right? Ohm's law says E is equal to I times R, right? R here would be the R net. So that would be 900 plus 100, that is 1000, right? Series combination. So the I in this circuit going in this direction, so it's going in this direction, the current, would be E divided by R net. So that would be 1 volts divided by 1000 ohms. That comes out to be 0.001 amps, right? Pretty straightforward, right? Hang on. Alright, so let's find the potential difference between points D and A going in this direction. So I'm going clockwise in this direction, alright? Going this direction. So VD, so I'll just remove this. So VD minus VA would be equal to I times R2. So that would be 0.001 times R2. That would be plus 0.9 volts, right? And similarly, what about going from point D to point A in this direction? So I'm now calculating the potential difference of between VD and VA going in this direction. So now I'm going in this direction, right? So that would be VD minus VA is equal to 1 minus I times R1, which again comes out to be 0.9 volts again. So you learn nothing new here, right? Let's go on and move further, alright? So suppose I have, instead of the battery, so let's get rid of this battery, and instead I connect the two resistors together. Okay, so connect them together, and so everything is the same. R2 900 ohms, R1 blah 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 100 ohms, D and A. And instead of the battery, I have with me a solenoid that is producing a magnetic field in this direction. So it's coming towards you. The magnetic field produced by the solenoid is going like this, right? So don't worry if you don't know what a solenoid is. For now, let's just say that a solenoid is something that produces a magnetic field or a changing magnetic field in our case right here. So let's say, so we denote a magnetic field going towards you by this symbol, right? So it's coming towards you. Let's now calculate again the potential difference between point D and point A. By the way, before we go on further, let me introduce you to a brief review that I prepared for you, and it goes over Faraday's laws and a little bit about conservative and non-conservative fields, which I think would be useful for you for the rest of the video. So let's go on and do this review first. So let's start with Faraday's laws first. What Faraday's law says is that suppose I have so I'm moving with this half of the page, and then I'll move onwards again, alright? So don't worry about anything here right now. So if I have a conducting loop or a wire, a closed loop in a in any field, so I have a conducting loop in a magnetic field, and what Faraday's law says is that the change in flux, what flux is flux is defined as the integral of B dot dA of a closed surface. So this is a closed surface, so supposing I have a closed surface like this, the plane of the loop, and this is a magnetic field around it, the magnetic flux denoted by phi B would be equal to the integral of B dot dA of that closed surface. So this is the closed surface I took here. You could take any other closed surface enclosing it, but the flux is defined in this way, right? So what Faraday's law says is that the EMF there will be an induced EMF produced in this conducting loop if there is a change in the magnetic flux associated with a closed surface in that loop. All right. So the induced EMF, so this is induced EMF, equal to minus d phi by dt, and so that can be written as this. And we all know that E induced is the integral along a closed loop of E dot dl. Alright, so this is just a review. Let me move on and go to conservative and non-conservative fields for a moment. So what conservative fields are that conservative field means that if I am at point A, so this is point A, and I am traveling along any arbitrary path in a conservative field going back to the same point A, so I'm going here, coming back to the same point, the closed loop integral of f dot dl would be 0. That means, in other words, the work done by the conservative field, denoted by the dot product with dl of the conservative field, would be 0 if I go from point A and come back to the point again, as written here. Alright? In a non-conservative field, this will not be true. Going from point A, coming back to the same point A again in a non-conservative field would not be equal to 0. Alright, so that's pretty straightforward, simple review that I wanted you to know before we move onwards. Alright, back to our example again. So let's say in here I have a changing magnetic field such that a magnetic field such that there's a change in magnetic flux which results in an EMF E induced of 1 volt, right? So let's say it's our lucky day and we have at this moment an E induced of 1 volts, right, in this conducting loop, the wire, right? Okay. So let's see what happens when we go and take the potential difference between VD and VA going in this direction, right? Going in this direction. Alright. So VD minus VA is equal to I times R2. I would be again 1 volts divided by R1 plus R2, 900 plus 100. You get the same current here. Alright. So I times R2 would be just 0.001 amperes times 900 ohms. That gives you a value of 0.9 volts again. But wait a minute, what would happen if I move from point D to point A in this direction? So in this direction, right? What would happen then? We have a problem. We have a serious problem that going from point D to point A, VD minus VA, according to our normal method of calculating the potential difference, would be what? Would be minus I times R1. That would be 0.001 times 100 ohms. That would be minus 0.1 volts. Now look at this. VD minus VA is this. VD minus VA is this. Amazing, right? So let's think about what this would mean. So suppose I have a voltmeter. So I guess I made this a little bit too big, but you get the idea, right? So suppose I have a voltmeter and I connect this voltmeter to terminal A and to terminal D such that the positive terminal of the voltmeter is attached to D. And if I flip it over, so this, if I have positive terminal and negative terminal again, I would have a change in the value indicated by the voltmeter. So let's see, plus 0.9 indicated by the voltmeter, minus 0.1, plus 0.9, minus 0.1. This is mind-blowing. Can you think of what the reason would be for this bizarre behavior? So I'll give you a few minutes, so if you want, you might want to pause this video for a minute or two and think for yourself about the review and about what I just told you, and see if you can get the answer right. Alright, so I hope you had a try for that. I hope you tried to attempt the problem, and so let's go on and see what the answer is. Alright, so the real answer in this case is that the magnetic field produced by the solenoid is not an example of a conservative field. Here the field is non-conservative, which means that traveling along a closed loop from point D to point A back to point D would not give me zero. The E.dl would not give me zero in this case. Alright, so let's see what happens in this case. So if I go from point D to point A, so that would be plus 0.9 volts, and then I go from the potential difference. So potential difference from going from point D to point A, VD minus VA, then going from A to D, so that potential difference going from A to D, VA minus VD, going like this, would be what? So this would be 0.9 volts. VA minus VD is just the opposite of this, so that would be plus 0.1 volts, right? That would come out to be plus 0 plus 1 volts, right? This is counterintuitive, because going along a closed loop from point D back to point D doesn't give 0 volts. So this is not equal to 0. So what did we learn? We learned that Kirchhoff's laws, which says that the closed loop integral of E.dl moving along a closed loop is not equal to 0 for cases of non-conservative fields. So don't always be blind and use Kirchhoff's rule in any circuit that you find, because that would not be true in case of changing magnetic flux associated in the circuit that you're working on. Alright, so I talked about the voltmeter with you, which was such a bizarre behavior. What was found when an experiment was done, or a demo was done, was I'll tell you in a moment, was that we connected two voltmeters. So these are two identical voltmeters connected to the same exact terminals. So this is connected from positive terminal to the negative terminal, and this again is connected to the positive terminal and to the negative terminal. So this is let me change this. So let me put it like this. So we have a positive terminal here, and let's say this is V1. Alright, so I put V1 as a voltmeter to the left, right, and V2, so let's say this is positive and this is negative, and this is V2. Alright, so this voltmeter is V2, and I connect the same two voltmeters on either side. What we found in the experiment conducted was something very bizarre, and that's what I'm going to show you in a moment. What we found out was the following graphs. The following graphs were found when we connected the two voltmeters together. So we were measuring a magnetic field. So the magnetic field produced by our solenoid was such as this. So this was the magnetic field that our solenoid was producing, right? And so you'll obviously notice that this magnetic field rises to a point and then saturates out to a level. dB by dt would be a curve like this and level out to 0, right? This is dB by dt, dB by dt, and it's proportional to E and is therefore proportional to I, right? By Ohm's law. So what we would observe, what we would think to observe, that by the way, we found that the change in magnetic flux at this point, at this beginning, was 0.1 volts. This was because the change in magnetic field was about 10 Tesla per second, and the area of the loop associated was 10 raised to the power minus 2 meter square, right? So that resulted in a change in magnetic flux of 0.1 volts at this instant, so at the beginning, right? Okay, so I called, so we had in our scenario we had the 2 voltmeters like this, right? To the right was V2, to the left was V1, right? So similarly, to the right was V2 and to the left was V1, right? Left, right, okay? And I'll just rewrite this for you. V2 was I times R2 and V1 was minus I times R1, right? What we would expect to see by the voltmeters, in the voltmeters, would be something like this. So I times R2, so we would expect, since R2 was 900 ohms, so we would expect something like this for V2 and something like this for V1. And in reality, when we did the experiment, we found a bizarre behavior such as this. Now don't worry about the ripples here, we won't address that here, and so note that at this particular moment of time, this voltage and this voltage was different. That means the right voltmeter and the left voltmeter were measuring different voltages at the same time. Amazing, right? Unbelievable. Alright, as a final note, I'd just like to, so this is what we saw. Right? So as a last takeaway message, before you go, would be this note that I wanted to share with you. Okay, so I wanted to discuss a consequence with you, a consequence of this video. Okay, remember, whenever we deal with a circuit which has to do with an ideal inductor. So an ideal inductor, so let's say we have a circuit with voltage V, we have a switch, we have an ideal inductor, and we have a resistor. Didn't do too much justice to it, but let's see. Okay, so we have a resistor here and inductor here. An ideal inductor is made of a superconducting material, and it has zero electric field inside. So E inside the inductor, inside an ideal inductor, would be 0. Okay, this is an ideal inductor. So this is the negative terminal, the positive terminal. Inside the battery, in the internal of the battery, the electric field would point from positive to negative. So this is inside the battery. The E field would point like this, and let's say that since the current would be going in this direction, we have an electric field inside the resistor in this direction. Okay? Alright. So note, whenever the graph for the current in this circuit would be something like this, right? The inductor wouldn't like to just take in all the current. It'll have some it'll try to, it won't let the current go instantaneously up to its maximum value, so it'll offer some inertia. Inertia was the word I was looking for. So when we do the closed loop integral of E dot dl, which is equal to, we all know now that would be equal to d phi b by dt and not 0 if there is a change in magnetic flux, such as here, we would, writing a closed loop integral of E dot dl from this point back to the same point again would be 0. Note, important, 0 because there is no electric field inside, and so E dot dl would be 0. Going here, plus I times R. E field is E field is in this direction, dl is in this direction, E dot dl is positive, right? So I times R minus V, E is in this direction, dl is in the opposite direction, is equal to minus L di by dt, and this is the place where most people get confused. So please note of this fact, alright? So thanks for watching the video. I hope you learned something from it. See you next time. Thanks.